Hello and welcome to the channel. Tonight we're stepping into the gentle world of cosmic collisions. Imagine two ancient dancers in the darkness of space, circling each other for millions of years in a slow, inevitable waltz toward union. When these titans finally embrace, they create ripples that stretch across the very fabric of reality itself, sending whispers through space-time that we can now hear as the universe's most profound song. Tonight we explore these moments when gravity becomes poetry, cosmic events that unfold one patient moment at a time. Before we begin, if you enjoy drifting off to the gentle hum of science, I'd be very grateful if you tap the like button and subscribe to the channel. It helps more sleepy minds find their way here. And while you're settling in, I'd love to know where you're watching from and what time it is for you right now. Feel free to share it in the comments. It's always wonderful to see how far these quiet little journeys reach, so get cozy. Let your shoulders relax, let your thoughts slow down like gravitational waves spreading gently through the vastness of space. Have you ever watched two dancers moving across a stage, so focused on each other that the rest of the world seems to disappear? There's something beautiful about that kind of singular attention, the way gravity works between two massive objects floating in the darkness of space. Tonight, we're going to explore one of the universe's most extraordinary performances, when two black holes, those mysterious giants that devour light itself, find each other in the cosmic dark and begin an ancient dance that ends in the most powerful collision the universe knows how to create. But here's what makes this story so fascinating. It's not really about destruction at all. It's about transformation, about the universe's way of whispering its deepest secrets through the bending of space and time itself. And remarkably, we've learned to listen. So settle in, let your breathing slow, and let's drift together into a story that begins with two lonely giants, separated by distances we can barely imagine, yet somehow destined to find each other in the infinite dark, the dance of gravity. How black holes find each other. Picture this. You're standing in a completely dark room so vast that you can't see the walls. Somewhere in that darkness there's another person, also standing alone. Neither of you can see the other, yet somehow you both begin to feel a gentle pull, like an invisible thread drawing you together across the emptiness. This is how black holes find each other in space. Not through sight, because light cannot escape their gravitational embrace, but through something far more fundamental. Gravity, that quiet architect of the universe, reaches across millions or even billions of miles, whispering to one massive object about the presence of another. But let's back up for a moment and think about what we're really talking about. A black hole isn't exactly a hole, despite its name. It's more like, imagine if you could take the mass of our sun and compress it down to a single point. Not a tiny marble, not a grain of sand, but literally a point with no size at all. The gravity becomes so intense that it warps the fabric of space and time around it like a bowling ball placed on a stretched rubber sheet. When two of these cosmic giants exist in the same galaxy, and galaxies are unimaginably large places, mind you, they don't immediately rush toward each other, like magnets. The universe is far more patient than that. Instead, they exist in their separate domains for millions, sometimes billions of years, each ruling over their own small kingdom of darkness. But gravity is persistent in the way that water is persistent, always finding a way, always working, never stopping. If these two black holes happen to be close enough, and close enough in cosmic terms might mean they're separated by distances thousands of times greater than the distance between Earth and our Sun, gravity begins its slow, inexorable work. The larger of the two black holes, if there's a size difference, acts like the lead dancer. Its gravitational field reaches out further, and the smaller black hole begins to feel that gentle tug. It's not dramatic at first. The smaller black hole might take millions of years just to change its path slightly, curving its trajectory through space, in a way that brings it just a little bit closer to its massive partner. And here's where the story becomes almost romantic, in a cosmic sense. As the smaller black hole adjusts its path, it's not moving in a straight line toward the larger one. Instead, it begins to trace what astronomers call an elliptical orbit, a stretched-out oval that brings it sweeping in closer, then farther away, then closer again, like a cosmic waltz played out over astronomical time. During these early stages of their gravitational courtship, both black holes continue their normal activities. They might still be feeding on nearby gas and dust, growing larger and more massive. They might be influencing the orbits of nearby stars, occasionally capturing one in their gravitational web. But increasingly, their attention turns toward each other. Interestingly, this process can be helped along by a third partner, another massive object, like a star or even a third black hole. Sometimes these cosmic matchmakers can alter the orbits just enough to bring our two dancers closer together, accelerating a process that might otherwise take longer than the current age of the universe. The gravitational waves, those ripples in space-time itself that we'll talk more about later, begin here, in these early orbits, but they're incredibly faint, like whispers so quiet, you'd need the universe's most sensitive ears to hear them. The black holes are still too far apart, their dance too slow and gentle, to create the dramatic songs they'll eventually sing. But with each orbit, something magical happens. The black holes lose a tiny bit of energy to these gravitational waves, like dancers gradually getting tired. As they lose energy, their orbit gets smaller, bringing them closer together. It's a feedback loop that will eventually become the universe's most spectacular crescendo during this phase, which can last for millions of years. The black holes are performing what scientists poetically call the in-spiral, a gradually tightening spiral that brings them ever closer together. The word itself sounds like a gentle inward breath, doesn't it? As if the universe is slowly drawing these giants toward their ultimate unity. What's remarkable is that during most of this time, if you could somehow observe these black holes from a safe distance, they would appear almost serene. There's no violence, no dramatic explosions, just two dark regions of space moving in their ancient pattern, invisible, except for their influence on anything nearby that does emit light. The stars in their vicinity begin to notice, of course. Their orbits become more complex, influenced by not one, but two massive gravitational sources that are themselves moving. Some stars might get ejected entirely from the area, flung out into space by the complex gravitational dynamics. Others might settle into new, stable orbits around the pair. And through it all, space itself is learning to bend in new ways. The gravitational field created by two massive objects orbiting each other is more complex than the field around a single black hole. It's like the difference between ripples created by dropping one stone in a pond versus dropping two stones simultaneously. The wave patterns interact, creating interference, creating beauty in the mathematics of their motion. As our two cosmic dancers continue their patient spiral inward, they remain unaware that billions of years in the future, creatures on a small blue planet will build machines sensitive enough to detect the songs they're beginning to sing. Space-time tides. The cosmic choreography before impact. Have you ever stood at the ocean's edge during a storm and felt the way the tide seems to breathe, pulling the water out, then pushing it back in, with a rhythm so deep it seems to come from the earth itself? There's something hypnotic about that back and forth motion, the way it shapes everything it touches without ever seeming hurried. This is what happens to space-time itself as two black holes draw closer together in their cosmic dance. The very fabric that Einstein taught us to think of as flexible, space and time woven together into something that can bend and stretch and ripple, begins to experience its own kind of tide. But let's slow down and really think about what we mean when we say space-time bends. It's one of those concepts that sounds almost magical until you let it settle in your mind like sediment in still water. Einstein showed us that what we experience as gravity isn't really a force pulling objects together. Instead, mass, especially very large amounts of mass, creates curves in space-time, and objects simply follow the straightest possible path through those curves. Imagine you're walking across a field at night with a flashlight, trying to walk in a perfectly straight line. But the field isn't flat, it's full of gentle hills and valleys that you can't quite see. Your straight line becomes a winding path as you naturally follow the contours of the landscape beneath your feet. This is what planets do as they orbit stars, and what our two black holes are doing as they spiral toward each other. But when you have two extremely massive objects orbiting each other, something beautiful and strange happens to the landscape of space-time around them. Instead of one simple bowl-shaped depression, like what you'd get around a single black hole, you get something more like, imagine two whirlpools in a river, spinning closer and closer together. As our black holes continue their in-spiral, the space-time around them begins to develop what physicists call tidal effects. Just as the moon creates tides in Earth's oceans by pulling more strongly on the water closest to it, the orbiting black holes create tides in the fabric of space-time itself. These aren't the kind of tides you could see with your eyes, of course. Space doesn't have a surface that rises and falls like water. Instead, the tidal effects show up in the way distances themselves stretch and compress in a rhythmic pattern. If you could somehow place a perfectly rigid ruler in the space between our orbiting black holes, you'd find that the ruler itself would be gently stretched and compressed twice during each orbit. The effect is incredibly subtle when the black holes are still relatively far apart, far more gentle than the tides our moon creates in Earth's water. But as the spiral tightens, as the black holes move closer and faster in their dance, these space-time tides grow stronger and more complex. Think of it like this. If you've ever watched figure skaters performing a pairs routine, you know how they start far apart, moving slowly, and then gradually come closer together as their routine builds to its climax. The movements that seemed gentle and flowing when they were far apart become more intense, more dramatic, as they spin closer together. The same thing happens with our black holes, except instead of air moving around the skaters, it's space-time itself that's being set in motion. The mathematics of this cosmic choreography is stunningly beautiful. As the black holes orbit each other, they create what's called a quadrupole pattern in the space-time around them. Imagine fourfold symmetry like a four-petaled flower that's constantly rotating. This pattern propagates outward from the orbiting pair like ripples spreading across the surface of a pond, except these ripples are traveling at the speed of light through the dimension of space-time itself. During this phase, which can last for thousands of years as the black holes get closer and closer, the universe around them begins to change in subtle ways. Any particles of matter caught in the tidal field would find themselves gently accelerated and decelerated in complex patterns. Stars in the vicinity would experience tiny but measurable changes in their orbits. Even empty space itself would ring like a bell, with gravitational waves too faint for our current instruments to detect. What's particularly fascinating is how the black hole's own structure begins to respond to these tidal forces. You might think that black holes, being some of the most extreme objects in the universe, would be rigid and unchanging. But they're not. They're more like liquid drops held together by their own gravity. As they orbit each other, tidal forces begin to distort their shapes, pulling them into slight elliptical forms that stretch toward their partner with each close approach. The event horizon, that invisible boundary around each black hole beyond which not even light can escape, begins to fluctuate and ripple. It's still perfectly black, still impossible to see directly, but its shape becomes more complex, more dynamic, like two soap bubbles that haven't quite touched yet, but are already beginning to influence each other's form, and through it all, the gravitational waves grow stronger. What started as whispers in the fabric of space-time become murmurs, then clear tones. The universe is beginning to learn the song that these two dancers will eventually sing at the moment of their union. If you could somehow listen to these waves, and remarkably we can, using instruments so sensitive they can detect changes in distance smaller than 1/10,000th the width of a proton, you'd hear something like a slow, deep drumbeat gradually getting faster and louder. Scientists call this the chirp pattern, and it's one of the most beautiful sounds the universe knows how to make. The black holes themselves remain invisible, of course. No light escapes from them to tell us directly what's happening, but their gravitational influence on spacetime creates a signature as unique as a fingerprint, a pattern of waves that carries information about their masses, their spins, even their history across billions of light-years of space. As they continue to spiral inward, the time between their closest approaches grows shorter. What might have been centuries between close passes becomes decades, then years, then months. The cosmic choreography is accelerating toward its climax, and the universe itself has become their stage, resonating with the rhythm of their ancient dance. But they haven't collided yet. They're still separate, still distinct, still performing their spiral ballet in the darkness. The real drama, the moment when two becomes one, is still ahead of us in our story, the final spiral, when orbit becomes doom. There's a moment in every dance when the partners know, without speaking, that the gentle movements of the beginning are about to transform into something far more intense. If you've ever watched ice dancers perform, you know that moment when they transition from graceful, flowing movements to the rapid spins and leaps that take your breath away. The music grows urgent, the movements become precise and powerful, and suddenly you're watching something that feels less like a performance and more like a force of nature. This is what happens to our two black holes as they enter the final phase of their billion-year courtship. After eons of patient spiraling, taking centuries or millennia to complete each orbit, they suddenly find themselves in a cosmic race toward an inevitable conclusion. The transition happens faster than you might expect. When the black holes are still separated by a distance of perhaps 10 or 20 times their own size, imagine two dancers still arm's length apart. Their orbit might take several minutes to complete. They're moving at perhaps 10% the speed of light, which sounds incredibly fast until you remember that we're talking about objects so massive that our sun would seem like a grain of sand by comparison. But as they spiral closer, the mathematics of gravity and orbital mechanics creates what physicists call a runaway process. Each orbit brings them closer together, which makes gravity stronger, which makes them orbit faster, which makes them lose energy to gravitational waves more quickly, which brings them even closer together. It's like water circling down a drain, but instead of water, it's the fabric of space-time itself that's being pulled into an ever-tightening spiral. During these final moments, and moments here means perhaps the last few seconds or minutes of a dance that has lasted longer than complex life has existed on Earth, the black holes begin to orbit each other hundreds of times per second. Imagine trying to follow a dance so fast that the partners complete an entire waltz in the time it takes you to blink. At these incredible speeds, the black holes are no longer separate entities influencing each other from a distance. They've become parts of a single, dynamic system. Their gravitational fields have merged into something new, something that doesn't exist anywhere else in the universe. The space-time around them isn't just curved, it's twisted, knotted, rippling with waves so powerful that they carry away energy equivalent to the light output of all the stars in the observable universe. But here's what makes this moment so remarkable. Despite all this incredible violence in the fabric of space-time itself, if you could somehow watch from a safe distance, you still wouldn't see anything. No light, no explosion, no dramatic visual effect, just two regions of perfect darkness, spinning around each other so fast that they blur together into a single shadow against the stars. The event horizons, those invisible boundaries that define the edges of the black holes, begin to stretch and distort in ways that challenge our understanding of what a black hole even is. As they orbit each other at these incredible speeds, tidal forces pull each black hole into an elongated shape, like two teardrops reaching toward each other. The smooth, spherical event horizons of solitary black holes become complex, dynamic surfaces that ripple and flow like liquid mercury. And then something truly extraordinary happens. At the moment when the black holes are separated by only a few times their own diameter, when they're orbiting each other at perhaps half the speed of light, the mathematics of Einstein's general relativity predicts something that sounds almost like science fiction. The event horizons touch and merge before the black holes themselves do. Think about that for a moment. The boundary that defines where each black hole begins and ends, that invisible surface beyond which nothing can escape, reaches out and connects with its partner, while the dense cores of the black holes are still technically separate. It's as if the shadows of two dancers joined hands before the dancers themselves embraced. This creates what scientists call a common event horizon, a single, complex surface that now encompasses both black holes. From this moment forward, anything that falls past this boundary is doomed to fall toward not one, but both black holes simultaneously. The geometry of space inside this merged event horizon becomes so complex that our usual notions of here and there begin to break down. During these final moments, the gravitational waves being produced are beyond anything else in the universe. If you could convert the energy being radiated away as gravitational waves into visible light, it would outshine every star, every galaxy, every quasar in the observable universe combined. The power output during the final second of the merger is equivalent to converting several solar masses directly into pure energy, all in the form of ripples in space-time itself. These waves race outward at the speed of light, carrying with them the story of what's happening at the center of this cosmic drama. They stretch and compress space itself as they pass, creating a signal so distinctive that scientists can reconstruct the entire final dance just by listening to these ripples with instruments sensitive enough to detect changes in distance, smaller than a proton. The frequency of these gravitational waves increases rapidly as the spiral tightens. What started as a slow, deep rumble becomes a rising chirp, climbing in pitch like a cosmic siren. If you could hear it directly, it would sound like a drop of water falling into a deep well, starting as a low whistle and ending in a sharp pop as the black holes finally merge. But even as this cosmic crescendo builds toward its climax, there's something almost serene about the physics involved. Despite the incredible energies and speeds, everything follows the elegant mathematics that Einstein laid out more than a century ago. The black holes aren't fighting against each other or struggling to escape their fate. They're simply following the straightest possible paths through spacetime, paths that happen to curve inevitably toward unity. In the final milliseconds, as the event horizons merge completely, and the dance becomes a singular cosmic phenomenon, the black holes cross a threshold from which there can be no return. Two separate cosmic entities, each with its own history stretching back perhaps billions of years, become one. The spiral that began so gently, so patiently, reaches its inevitable conclusion not with violence but with a kind of cosmic inevitability that feels almost peaceful. And then, in an instant that lasts perhaps a few hundredths of a second, something new is born from their union, a single, more massive black hole that will spend the next several minutes learning how to exist as one entity instead of two. Ripples in reality. How collisions send gravitational waves. Have you ever dropped a stone into perfectly still water on a quiet morning? There's something mesmerizing about watching those concentric circles spread outward, carrying the story of that single moment to the edges of the pond. Each ripple is a messenger, telling distant shores about the stone, about the moment of impact, about the energy that was released when solid met liquid. This is exactly what happens when black holes collide, except instead of ripples spreading across the surface of water, we get ripples spreading through the very fabric of spacetime itself. These gravitational waves are perhaps the most elegant messengers the universe knows how to create, carrying news of cosmic events across billions of light years without losing their essential story. But let's begin with what Einstein himself struggled to believe. When he first developed his theory of general relativity in 1915, the mathematics suggested something that seemed almost too strange to be real, that accelerating masses should create waves in spacetime, much like accelerating electric charges create electromagnetic waves. For years, even Einstein himself wasn't sure whether these gravitational waves were a real physical phenomenon or just a mathematical curiosity. The key insight is beautifully simple, once you let it settle in your mind. Remember that spacetime isn't empty, nothingness. It's a real physical thing that can be stretched, compressed, twisted, and set into motion. When our two black holes spiral around each other, they're not just moving through space, they're stirring spacetime itself like a cosmic spoon stirring honey. Imagine you're holding a large sheet, stretched tight between your hands. If you move your hands up and down in a gentle rhythm, waves will travel across the surface of the sheet. The sheet itself isn't moving from place to place, but the pattern of its stretching and relaxing propagates outward as a wave. This is remarkably similar to what happens with gravitational waves, except the sheet is the three-dimensional fabric of space itself, plus time as a fourth dimension. As our black holes perform their final spiral dance, they create what physicists call a quadrupole pattern in spacetime. If you could somehow see gravitational waves, they would look like a four-petaled flower pattern rotating around the orbiting black holes. Two of the petals represent regions where space is being stretched in one direction, while the other two represent regions where space is being compressed in the perpendicular direction. This pattern propagates outward at exactly the speed of light, not because gravitational waves are made of light, but because the speed of light is really the fundamental speed limit of the universe, the maximum rate at which any information can travel from one place to another. These waves carry information about their source embedded in their very structure, the masses of the colliding black holes, how fast they were spinning, even details about the final moments of their merger. But here's what makes gravitational waves so remarkable and so difficult to detect. They're incredibly weak by the time they reach us. The black hole collision that created the waves might have released more energy in gravitational waves than all the stars in the observable universe emit as light. But after traveling for millions or billions of years across space, the waves arrive at Earth, causing changes in distance smaller than 1/10,000th the width of a proton. To put that in perspective, if you could measure the distance from Earth to the nearest star with perfect accuracy, a gravitational wave would change that distance by less than the width of an atom. It's like trying to detect the motion of a single grain of sand on a beach by measuring the position of the moon. Yet remarkably, we can detect these waves. The secret lies in understanding exactly how gravitational waves affect matter as they pass by. Unlike sound waves, which push air molecules back and forth, or water waves, which lift and lower the surface of the ocean, gravitational waves stretch and compress space itself. Imagine you're floating in space with a friend, separated by exactly 1 kilometer. As a gravitational wave passes through you, that kilometer distance would oscillate, first stretching to become perhaps 1 kilometer plus the width of a proton, then compressing to become 1 kilometer minus the width of a proton. You and your friend wouldn't feel anything, because your bodies would be stretched and compressed along with space itself. But if you had a way to measure the distance between you with incredible precision, you could detect these tiny oscillations. The waves arrive in a characteristic pattern that tells the story of the collision. When the black holes are still relatively far apart, orbiting slowly, the gravitational waves are weak and low frequency like a deep, quiet drum beat. As the spiral tightens and the orbital frequency increases, the gravitational waves grow stronger and higher in frequency, creating what scientists poetically call a chirp, a sound that rises in pitch, like a bird's song. The final moments of the collision create the most distinctive signature of all. As the black holes merge, there's a sudden burst of gravitational waves, the cosmic equivalent of a cymbal crash, followed by what's called the ringdown, where the newly formed black hole settles into its final stable configuration like a bell gradually stopping its vibration after being struck. What's beautiful about this process is how it transforms something invisible and unimaginably distant into something we can, in a sense, hear. The mathematical techniques scientists use to extract gravitational wave signals from detector data are very similar to those used in audio processing. They can filter out noise, enhance weak signals, and even convert the wave patterns directly into sound waves that human ears can perceive. When you listen to the audio representation of a black hole merger, and you can find these recordings online, you hear something that sounds remarkably organic. The rising chirp followed by the final pop sounds almost like a raindrop falling into water, or like a whip being cracked, or like the call of some cosmic bird singing a song of transformation across the vast darkness of space. These waves carry another kind of beauty too. They're completely unimpeded by anything in their path. Light from distant cosmic events can be absorbed by dust, scattered by gas clouds, or blocked entirely by intervening objects. But gravitational waves pass through everything, planets, stars, entire galaxies, without losing their message. They provide us with a completely transparent view of some of the universe's most extreme events. And here's something that might give you a gentle sense of wonder as you drift towards sleep. Gravitational waves from black hole collisions are passing through your body right now. The waves from mergers that happened millions of years ago are stretching and compressing the space between the atoms in your cells by amounts so tiny that they have no effect on your biology. But the information they carry about distant cosmic dances is encoded in the very geometry of the space you occupy. The universe, it turns out, is constantly whispering its secrets to us through these ripples in reality. We just had to learn how to learn the loudest event in the universe, yet utterly silent. There's something almost poetic about the way the universe keeps its most dramatic secrets. If you've ever been to a fireworks display, that moment of anticipation when you see the bright flash in the sky, but haven't heard the boom yet. Sound traveling so much slower than light that there's this beautiful pause between seeing and hearing, between the visual spectacle and the auditory confirmation of what just happened. Black hole collisions are the opposite of fireworks in the most fascinating way. They represent the loudest events the universe knows how to create, releasing more energy in their final seconds than all the stars in the observable universe combined, yet they happen in perfect, absolute silence. Let's think about what we mean when we talk about sound, and why that matters for understanding these cosmic collisions. Sound, as we experience it, is really just pressure waves traveling through air. When you clap your hands, you compress the air between your palms, and that compression travels outward like ripples in a pond, eventually reaching your eardrums and creating the sensation we call hearing. But space, that vast expanse between stars and galaxies, is essentially empty, not perfectly empty, mind you. Even the vacuum of space contains a few atoms per cubic meter, along with magnetic fields, cosmic rays, and other phenomena. But it's empty enough that sound waves, as we understand them, simply cannot exist there. There's no medium dense enough to carry pressure waves across the cosmic distances that separate us from colliding black holes. So when two black holes, each perhaps 30 times more massive than our Sun, spiral into each other at half the speed of light, releasing the gravitational wave equivalent of several solar masses worth of energy in just a few seconds. It all happens in the most profound silence imaginable. If you could somehow survive being positioned a safe distance away, perhaps a few thousand light years, we would witness the most energetic event in the local universe, while hearing absolutely nothing at all. Yet, in another sense, these collisions are incredibly loud. The gravitational waves they produce carry energy across space, much like sound waves carry energy through air. When these waves finally reach Earth and pass through our gravitational wave detectors, scientists can convert the wave patterns into audio frequencies and play them through speakers. What you hear is, in a very real sense, the sound of space-time itself ringing like a cosmic bell. This raises a beautiful question. If a black hole collision happens in the vacuum of space, does it make a sound? The answer is both no and yes, depending on how you define sound. No, in the traditional sense, because there's no air or other medium to carry acoustic waves, but yes, in the sense that the gravitational waves carry the same kind of information that sound waves do, encoded in patterns of compression and expansion that we can decode and listen to. The loudness of a gravitational wave event is measured differently than the loudness of conventional sound. Instead of decibels, scientists talk about the strain amplitude, how much the gravitational wave stretches and compresses space as it passes by. The most powerful black hole mergers detected so far have strain amplitudes of about 10 more from 21, which sounds incredibly small until you realize this represents changes in distance, smaller than 1/10,000th the width of a proton, yet spread across detector arms that are several kilometers long. To put this in perspective, if you scaled up a gravitational wave detector to the size of the solar system, the strongest black hole merger signal would cause changes in distance equivalent to about the width of a human hair. The universe whispers its most dramatic stories in voices so quiet they challenge the very limits of what's physically possible to measure. What makes this silence even more profound is the violence of what's actually happening. During the final moments of a black hole merger, the space around the collision is experiencing forces that would instantly destroy any form of matter we can imagine. The tidal forces alone would stretch and compress atoms to the point where the very concept of atomic structure becomes meaningless. Temperatures and pressures reach values that existed nowhere in the universe since the first moments after the Big Bang. If there were somehow rocky planets orbiting these black holes, which there couldn't be, for reasons we'll explore later, they would be torn apart not by heat or explosive forces, but by the stretching and compressing of space itself. Mountains would rise and fall as gravitational waves passed through them. Oceans would slosh back and forth with tides so extreme they would boil away into space. Yet all of this would happen in absolute silence, with no acoustic signature to mark the destruction. This silence extends beyond just the absence of sound waves. Black holes, by their very nature, absorb electromagnetic radiation rather than emitting it. So there's no flash of visible light, no burst of radio waves, no X-ray fireworks to mark the moment of collision. The merger happens in a darkness so complete that if you were watching from a spacecraft a few light years away, you would see absolutely nothing. Just empty space, where two invisible objects happen to be performing the universe's most energetic dance. The only signals that escape to tell us about these cosmic events are the gravitational waves themselves, racing outward at the speed of light, carrying the story encoded in the stretching and compressing of space-time. In a sense, gravitational waves are the universe's way of talking to itself, a language written not in light or sound or any form of matter, but in the geometry of space and time itself. And here's what's particularly beautiful about this cosmic silence. It preserves the purity of the gravitational wave signal, because there's no other radiation escaping from the collision, no electromagnetic interference or acoustic noise. The gravitational waves carry an incredibly clean signature of exactly what happened. It's like being able to hear a single instrument playing in perfect acoustic isolation, every note clear and distinct. When scientists first detected gravitational waves from black hole mergers, they described the experience as suddenly having a new sense. For the entire history of astronomy, we had been like creatures who could see but not hear, watching the universe's drama unfold in visual silence. Gravitational wave astronomy gave us ears for the first time, allowing us to listen to cosmic events that had always been happening around us, but in frequencies and through media we had never learned to perceive. The irony is delicious. The loudest events in the TEDx happen in perfect silence, yet they've given us an entirely new way to listen to the cosmos. In detecting these waves, We haven't just measured incredibly tiny changes in distance. We've learned to hear the universe singing songs we never knew existed. Melodies written in the stretching and bending of space itself. As you settle into sleep tonight, you might find it comforting to know that this cosmic silence surrounds us, always. The space between galaxies is filled with a profound quiet that no earthly noise can disturb, broken only by the occasional whisper of gravitational waves carrying news of distant cosmic dramas across billions of years of travel time. It's the deepest, most complete silence imaginable, and it holds all the universe's most powerful stories, measuring the invisible, LIGO, and the proof of a collision. There's something almost magical about the moment when the impossible becomes possible, when a dream that seems too ambitious to ever come true suddenly transforms into reality. It's like watching a master musician tune their instrument. At first, all you hear are discordant notes and rough approximations, but then suddenly, everything aligns, and the most beautiful, pure tone emerges from what seemed like chaos. This is the story of how human beings learnt to detect gravitational waves, and in doing so gave ourselves the ability to witness black hole collisions happening billions of light years away. It's a story that spans nearly a century, from Einstein's initial prediction to the moment in 2015 when scientists first heard the universe whispering its secrets through the bending of space itself. Let's begin with the almost absurd audacity of the idea. Imagine you're an engineer and someone comes to you with a proposal. They want to build a machine that can detect changes in distance smaller than 1/10,000th the width of a proton, using laser beams that travel back and forth along arms several kilometers long, all while filtering out the vibrations from truck traffic, earthquakes, ocean waves, and even the thermal motion of atoms in the detector itself. Your first response would probably be polite skepticism. Your second response might be to suggest that the person proposing this should perhaps consider a nice, relaxing hobby instead. Yet, this is exactly what the scientists and engineers behind LIGO, the Laser Interferometer Gravitational Wave Observatory, set out to accomplish. The basic principle is elegantly simple, even if the execution required pushing the boundaries of precision measurement to previously unimaginable limits. An interferometer works by splitting a laser beam into two perpendicular paths, sending each beam down a long arm where it bounces off mirrors and returns to the starting point. When the two beams recombine, they create an interference pattern that's exquisitely sensitive to any changes in the length of either arm. Under normal conditions, if nothing is disturbing the detector, the two laser beams travel exactly the same distance and return perfectly in phase with each other. But when a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction. Suddenly, one arm becomes slightly longer while the other becomes slightly shorter, and this tiny difference shows up as a change in the interference pattern of the recombined laser beams. The engineering challenges involved in making this work are staggering. The mirrors at the end of each arm must be isolated from every possible source of vibration. They hang from elaborate suspension systems that filter out seismic noise, temperature fluctuations, and even the tiny random pushes from air molecules. The laser light itself must be stabilized to a degree that would make a watchmaker weep with envy. Any fluctuation in the laser's frequency or intensity could masquerade as a gravitational wave signal. But perhaps the most beautiful aspect of LIGO is how it transforms the incredibly esoteric phenomenon of gravitational waves into something almost tangible. The detector doesn't just measure these cosmic ripples, it converts them into patterns that human beings can see on computer screens, analyze with mathematical tools, and even convert into audio files that we can literally hear with our ears. When LIGO detected its first gravitational waves on September 14, 2015, the signal arrived exactly as Einstein's equations had predicted it would, more than a century earlier. The characteristic chirp pattern, rising in frequency from about 35 Hz to 500 Hz over the course of 1/5 of a second, matched the theoretical predictions for two black holes spiraling into each other, with masses of approximately 30 solar masses each, located about 1.3 billion light-years away. What's remarkable is how clean and unmistakable the signal was. For decades, gravitational wave physicists had worried about how they would distinguish real cosmic signals from the endless background of instrumental noise and terrestrial interference. But when the first signal appeared in the data, it was so clear, so perfectly matched to theoretical predictions, that there was no ambiguity about what they were seeing. The detection happened almost simultaneously at both LIGO detectors. one in Hanford, Washington, and the other in Livingston, Louisiana, separated by about 3,000 kilometers. The gravitational wave took 7 milliseconds longer to reach Louisiana than Washington, which allowed scientists to triangulate the approximate location of the source in the sky. This time delay also provided crucial confirmation that what they were seeing was indeed a wave traveling at the speed of light across space, rather than some form of instrumental artifact. But let's step back and think about what this detection really represents. The collision they observed happened 1.3 billion years ago, when complex life on Earth was just beginning to emerge from single-celled organisms. The gravitational waves from that ancient cosmic event traveled across space for longer than multicellular life has existed on our planet, preserving within their wave pattern the precise details of what happened during the final moments of the black hole merger. In a very real sense, LIGO serves as a time machine, allowing us to witness events from the deep cosmic past with incredible fidelity. The waves carry information not just about the final merger, but about the entire in-spiral process, how the black holes found each other, how their orbital dance evolved over millions of years, even details about how much each black hole was spinning before the collision. The technology behind LIGO represents one of humanity's most impressive achievements in precision measurement. Each detector can sense changes in arm length equivalent to moving the nearest star by less than the width of a human hair. The mirrors are among the most perfect objects ever created by human beings, polished to reflect 99.999% of the laser light that hits them, with surface imperfections smaller than the wavelength of the light itself. Yet for all its technical sophistication, there's something beautifully simple about what LIGO does. It listens. In a universe filled with electromagnetic radiation across all wavelengths from radio waves to gamma rays, LIGO opened up an entirely new window, our first direct access to gravitational radiation, to information encoded not in photons or particles, but in the stretching and bending of space-time itself. Since that first detection in 2015, LIGO and its European counterpart, Virgo, have detected dozens more black hole mergers, along with the collision of two neutron stars. Each detection adds new chapters to our understanding of the universe's most extreme phenomena. We've discovered that black hole mergers are surprisingly common, happening somewhere in the observable universe perhaps once every few minutes. We've learned that black holes can spin at incredible rates, some rotating nearly as fast as Einstein's equations permit. We've even detected hints of black holes with masses that don't fit into the neat categories we thought we understood. But perhaps most importantly, gravitational wave astronomy has given us confirmation of something that seemed almost too beautiful to be true. Einstein's equations, developed more than a century ago, using nothing but thought experiments and mathematical insight, predict the behavior of the universe's most extreme environments with stunning precision. Every gravitational wave detection is essentially a field test of general relativity under the most extreme conditions imaginable. And so far, Einstein's century-old theory passes every test with flying colors. As you drift towards sleep, consider this. The gravitational waves from black hole collisions happening right now in distant galaxies are already on their way toward Earth. Some will arrive next year, some in 1,000,000 years, some in 1,000,000,000 years, each carrying the story of cosmic events so powerful they temporarily outshine the combined light output of all the stars in the observable universe. And increasingly, human beings are learning to listen to these cosmic songs, to decode the stories written in the stretching and bending of space itself. We've become a species that can hear the universe's heartbeat, can detect the whispers of space-time as it carries news of the most dramatic events the cosmos knows how to create. In learning to measure the invisible, we've discovered that the universe has been singing to us all along. The newborn black hole, heavier, faster, hungrier. There's something almost tender about the moment after birth, when a new life begins its independent existence. Whether it's a baby taking its first breath, a butterfly emerging from its chrysalis, or a star beginning to shine with nuclear fire, there's always a period of adjustment, of settling into new patterns of being. The same is true for black holes born from cosmic collisions, though their birth announcement comes in the form of gravitational waves racing across the universe at the speed of light. In the aftermath of a black hole merger, what emerges is not simply the sum of its parts. The newborn black hole carries the combined mass of its parents, minus the portion that was radiated away as gravitational waves during the final moments of collision. But it's also something entirely new, heavier than either of its parents individually, spinning faster than most black holes ever achieve on their own, and possessing what physicists playfully describe as an increased appetite for matter. Let's think about what heavier means in this context. When two black holes of say 30 solar masses each merge, you might expect the result to be a 60 solar mass black hole, but Einstein taught us that mass and energy are interchangeable, and during the final moments of merger, several solar masses worth of energy gets radiated away as gravitational waves. The newborn black hole might emerge with a mass of only 55 solar masses or so, still the most massive object in its local neighborhood, but carrying the signature of its violent birth in its slightly reduced mass. This missing mass represents one of the most dramatic energy releases in the universe. To put it in perspective, if you could somehow convert the entire mass of our sun directly into energy, it would produce less power than what's released in gravitational waves during the final second of a typical black hole merger. The newborn black hole literally glows with gravitational radiation, though glow isn't quite the right word since gravitational waves are invisible to every form of electromagnetic detector we have. The newborn black hole is also spinning, and often spinning very rapidly. This rotation comes from the orbital motion of the two black holes just before merger. All that angular momentum has to go somewhere, and it gets converted into the rotational motion of the newly formed object. Some newborn black holes emerge spinning at nearly the maximum rate that Einstein's equations allow, rotating hundreds of times per second despite being perhaps 50 kilometers across. A spinning black hole is a fundamentally different creature from a non-rotating one. The mathematics that describe it are more complex. The space-time around it is twisted and dragged along with the rotation, and its influence on nearby matter and energy is more dramatic. It's like the difference between a whirlpool in still water and a whirlpool in a rushing river. The moving current adds layers of complexity to the flow patterns. This spin gives the newborn black hole what we might call enhanced gravitational charisma. Its rotating mass twists spacetime around itself in a phenomenon called frame dragging, which means that anything trying to orbit the black hole gets pulled along in the direction of rotation, whether it wants to or not. It's as if the black hole has learned to dance with spacetime itself, leading a cosmic waltz that encompasses everything in its vicinity. The hunger of a newborn black hole isn't really hunger in any biological sense. Of course, black holes don't eat because they're hungry. They accrete matter because gravity is relentless, and anything that comes too close gets trapped beyond the event horizon. But newborn black holes, especially rapidly spinning ones, are particularly effective at capturing and processing nearby matter. Part of this enhanced appetite comes from the fact that the merger often occurs in an environment that's already rich with material gas, dust and debris that might have been orbiting one or both of the original black holes. The violent dynamics of the merger can disrupt these orbits, sending material spiraling inward toward the event horizon of the newborn black hole. But there's something more subtle happening too. A rapidly spinning black hole can extract energy more efficiently from infalling matter through a process called the Penrose mechanism. Material falling into such a black hole can actually gain energy by interacting with the rotational motion of space-time itself, sometimes producing jets of matter and energy that shoot outward at nearly the speed of light. These jets, when they occur, are among the most spectacular phenomena in the universe. Streams of particles accelerated to incredible energies, creating bright beacons that can be seen across billions of light years. Not every newborn black hole produces such jets, but when they do, they announce their birth to the entire observable universe, with displays of electromagnetic fireworks that complement the gravitational wave songs they sang during their formation. The newborn black hole also inherits a kind of cosmic memory from its parents. Embedded in its mass, spin, and other properties is information about where its parent black holes came from, how they lived their separate lives, and the circumstances of their final union. This information isn't lost. It's preserved in the structure of space-time around the new black hole, written in a language of curvature and rotation that physicists are still learning to read. For the first few minutes after its birth, the new black hole continues to ring with gravitational waves as it settles into its final configuration. This ring-down phase is like the cosmic equivalent of a newborn's first cries, announcement of successful birth and healthy vital signs. The frequency and pattern of these waves tell us precisely what kind of black hole has been born, its exact mass, its rate of rotation, even confirmation that it's actually a black hole rather than some other exotic object. But once the ring-down fades, the newborn black hole begins its long, quiet existence. Without the dramatic dynamics of merger, it becomes much harder to observe direct. It might go millions or billions of years before encountering significant amounts of matter to accrete. during which time it would be essentially invisible except for its gravitational influence on nearby objects. Yet even in this quiet phase, the newborn black hole continues to shape its environment in subtle but profound ways. Its gravity influences the orbits of distant stars, potentially disrupting planetary systems or shepherding the formation of new ones. Its presence affects the large-scale structure of its host galaxy, helping to regulate star formation and the flow of gas and dust through interstellar space. There's something almost meditative about contemplating the long life ahead of a newborn black hole. Unlike stars which burn brightly for millions or billions of years before dying, or planets which slowly cool and become geologically inactive, black holes exist on timescales that dwarf human comprehension. The newborn black hole will still be there when our sun has burned out, when the Milky Way has collided with Andromeda, when the universe itself has expanded and cooled to the point where new star formation has essentially ceased. During this vast lifetime, the black hole might encounter other black holes, beginning new orbital dances that could last longer than the current age of the universe before culminating in another merger. It might capture a companion star and spend millions of years slowly consuming it, creating spectacular displays of X-ray radiation as the stellar material spirals inward. Or it might simply drift through space, a dark gravitational anchor around which the cosmic drama of future epochs will unfold. In a sense, every black hole merger represents both an ending and a beginning. The two parent black holes, each with their own history stretching back perhaps billions of years, cease to exist as separate entities, but their union creates something new, a cosmic offspring that carries the combined legacy of its parents into a future so distant that the very concept of time begins to lose meaning. As you drift towards sleep, consider this. Somewhere in the universe right now, a newborn black hole is taking its first metaphorical breaths, settling into existence after a collision so powerful it briefly outshone all the stars in the observable universe combined. It spins in the darkness, heavier and more complex than either of its parents, ready to begin a journey through space and time that will outlast everything we can imagine. The universe has gained a new citizen, and the cosmic dance continues. The ring down, how the universe echoes the impact. Have you ever struck a bell and listened to the way the sound fades? There's something beautiful about that gradual decay, how the pure, strong tone slowly dissolves into silence, carrying with it the memory of the impact that created it. The mathematics of that fading sound are elegant and predictable. The frequency stays constant while the amplitude decreases exponentially, like a musical note written in the language of decay. This is exactly what happens after two black holes merge, except instead of sound waves traveling through air, we get gravitational waves propagating through the fabric of spacetime itself. The newborn black hole, distorted and complex from the violence of its birth, gradually settles into its final stable configuration. And as it does so, it rings like a cosmic bell, with a song that can be heard across the universe. Let's imagine what this settling process looks like, though looks isn't quite right, since black holes remain invisible, even during their most dramatic moments. Picture a drop of water falling into a perfectly still pond. For just an instant, the surface is chaotic, splash patterns and ripples interfering with each other in complex ways. But then, quite quickly, the disturbance settles into concentric circles spreading outward, carrying the energy of that initial impact in increasingly gentle waves. The ring down of a newborn black hole follows a similar pattern, but the surface that's settling is the event horizon itself, and the ripples are distortions in the curvature of spacetime. During the final moments of merger, the event horizon has a complex, ever-changing shape, stretched and twisted by the incredible tidal forces as the two black holes spiral together. But black holes, like drops of water, have a preferred stable shape, and natural forces work to restore that equilibrium. For an isolated, non-rotating black hole, that stable shape is perfectly spherical, as round and smooth as geometry allows. For a rotating black hole, which is what most merger products are, the stable shape is what mathematicians call an oblate spheroid, slightly flattened at the poles and bulging at the equator, like our Earth but much more subtly so. The ring-down process is essentially the event horizon learning how to achieve and maintain this ideal shape. But here's what makes the ring-down so musically beautiful. Just as a bell has characteristic frequencies determined by its size, shape, and material properties, a black hole has characteristic ring-down frequencies determined entirely by its mass and rotation rate. These frequencies are called quasi-normal modes, and they represent the natural harmonics of curved spacetime around a rotating black hole. Einstein's equations predict these frequencies with mathematical precision. Give a physicist the mass and spin of a black hole, and they can calculate exactly what the ringdown should sound like, which frequencies should be present, how quickly each frequency should decay, even the relative strength of different harmonics. It's like being able to predict the exact sound a bell will make, just by knowing its weight and how fast it's spinning. When LIGO detects the ringdown portion of a gravitational wave signal, scientists are essentially listening to spacetime itself resonating in its characteristic frequencies. The dominant tone corresponds to what physicists call the fundamental quadruple mode, the basic pattern of stretching and compressing that a rotating black hole imprints on the space around it. But there are overtones too, higher frequency modes that add richness and complexity to the gravitational wave song. The beauty of the ringdown lies partly in its universality. Every black hole merger, regardless of the specific masses or spins of the parent black holes, ends with this same type of exponentially decaying oscillation. The frequencies and decay rates vary. More massive black holes ring at lower frequencies, just like larger bells produce deeper tones, but the mathematical structure is always the same. It's as if nature has chosen a single, elegant way to transition from the chaos of collision to the stability of a merged system. The ringdown typically lasts only a fraction of a second as measured by our earthbound clocks, but it carries an enormous amount of information. By analyzing the frequency spectrum and decay rates, scientists can determine the mass and spin of the newly formed black hole with remarkable precision. They can also test whether the object that was created is actually a black hole at all, rather than some other exotic possibility predicted by alternative theories of gravity. This testing capability is particularly important because the ringdown frequencies are among the most precisely predicted phenomena in all of general relativity. Einstein's equations don't just suggest what the ringdown should look like, they specify it exactly, with no free parameters or uncertainties. When we observe a ringdown that matches these predictions to high precision, we're seeing one of the most stringent tests of general relativity ever performed. But there's something poetic about the ringdown beyond its scientific value. In those final moments, as the gravitational waves fade away, we're witnessing the universe's own process of healing after trauma. The violent collision that created chaos in the local spacetime gradually gives way to a new equilibrium, a new stability. The cosmos absorbs the shock of merger and finds its way back to a state that can persist for billions upon billions of years. The exponential decay of the ringdown also has a kind of mathematical music to it. Unlike the chirp of the inspiral, which rises in frequency like a cosmic siren, the ringdown maintains constant frequency while the amplitude fades away. If you could listen to it directly, it would sound like a pure tone gradually becoming quieter and quieter until it disappears into silence. Something almost peaceful about this progression from chaos to quiet, from the most energetic event in the local universe, to the profound stillness of stable spacetime. During the ringdown, the newborn black hole is essentially learning its own identity. The gravitational wave frequencies encode its vital statistics, mass, spin, even subtle details about its structure. In a sense, the ringdown is the universe's way of taking inventory after a major cosmic event, determining exactly what new object has been created and broadcasting that information to anyone with sensitive enough instruments to listen. The waves produced during ringdown travel outward at light speed, carrying this information across cosmic distances without degradation. The ringdown from a merger that happened a billion years ago reaches us with its frequency spectrum intact, allowing us to reconstruct the properties of a black hole that formed when the universe was significantly younger than it is today. As the ringdown fades into undetectability, the newborn black hole settles into its long, quiet existence. The dramatic gravitational wave emission essentially ceases, and the black hole becomes, for practical purposes, invisible to our current detection methods. It will influence nearby matter gravitationally, perhaps eventually accreting material, and becoming visible through electromagnetic radiation. But the spectacular gravitational wave concert is over. Yet the memory of that cosmic bell ringing will persist. The gravitational waves from the ringdown will continue racing through space for billions of years, carrying their message about this particular cosmic birth to regions of the universe so distant we cannot even see them. In some sense, the ringdown never truly ends. It just becomes too faint for anyone to hear, spreading its cosmic song through ever larger volumes of space-time. There's something deeply satisfying about this gradual return to stability. After all the violence and chaos of collision, after space-time itself was stretched and twisted beyond easy comprehension, the universe finds its way back to equilibrium, through processes that are both violent and peaceful, both dramatic and mathematically inevitable. As you listen to the cosmic quiet that surrounds us now, remember that it's punctuated regularly by these moments of ring-down, black holes throughout the universe, settling into stability after their births, each one ringing its own gravitational song into the darkness, adding its voice to the grand symphony of cosmic evolution that plays on scales of space and time, almost too large to imagine what we see when we can't see. Detecting the undetectable. There's a peculiar challenge that faces astronomers when they study black holes. How do you observe something that, by definition, cannot be observed? It's like trying to photograph a shadow that casts no shadow, or listening for a silence that makes no sound. Black holes absorb light rather than emitting it, bend space rather than occupying it, in any conventional sense, and exist in a realm where our normal concepts of visibility and detection simply don't apply. Yet remarkably, black holes turn out to be among the most detectable objects in the universe, precisely because of their profound effects on everything around them. They're like cosmic magicians who remain invisible while making spectacular things happen to their surroundings, leaving fingerprints of their presence written in the behavior of light, matter, and space-time itself. Before gravitational wave detectors like LIGO came online, astronomers had to be extraordinarily clever about finding black holes. They became cosmic detectives, looking not for the black holes themselves, but for the evidence of their presence, the way they influenced nearby stars, the dramatic light shows they created when feeding on surrounding matter, the subtle gravitational lensing effects they produced when they passed between us and distant background objects. One of the most beautiful methods involves watching binary star systems where one component has become a black hole. Imagine a cosmic dance where one partner is visible, a normal star shining with its own light, while the other partner is completely invisible. You can still detect the invisible dancer by watching how the visible one moves, the way it speeds up and slows down, the subtle wobble in its motion that reveals the gravitational influence of its dark companion. These binary systems sometimes become even more dramatic when the black hole begins feeding on its stellar partner. Matter doesn't fall straight into a black hole. Instead, it forms what's called an accretion disk, a swirling, superheated spiral of gas and plasma that can shine brighter than entire galaxies before finally disappearing beyond the event horizon. Picture a cosmic whirlpool where the water has been replaced by matter heated to temperatures of millions of degrees. The inner edge of this disk, where material makes its final plunge toward the event horizon, reaches temperatures so extreme that it glows with X-ray radiation. This creates one of the most distinctive signatures of an actively feeding black hole, a brilliant X-ray source that appears to be coming from empty space, marking the location of the invisible gravitational monster responsible for the spectacular light show. But perhaps the most elegant way we detect black holes is through gravitational lensing. Einstein predicted that massive objects would bend the path of light, passing near them, acting like cosmic magnifying glasses. When a black hole passes between us and a distant star, it can focus and amplify the star's light, creating characteristic patterns of brightening and dimming that serve as a gravitational signature of the black hole's presence. These lensing events are rare and unpredictable, but when they occur, they provide incredibly precise measurements of the lensing object's mass. It's like being able to weigh something invisible by watching how it bends light around it. Some of the most isolated black holes, those without nearby stars or gas to feed on, have been detected only through these chance alignments with background stars. The techniques for detecting black holes have become so sophisticated that astronomers can now map their effects with incredible precision. At the center of our own galaxy, stars have been observed orbiting an invisible object with such tiny, rapid orbits that the gravitational field required to contain them can only be explained by the presence of a supermassive black hole containing millions of times the mass of our Sun, compressed into a region smaller than our solar system. Watching these stars is like watching a cosmic clock, with orbital periods that can be measured to extraordinary precision. One star, designated S2, completes its highly elliptical orbit around the galactic center in just 16 years, reaching speeds of nearly 5,000 kilometers per second at its closest approach to the black hole. The precision of these orbital measurements allows astronomers to test Einstein's general relativity in the strongest gravitational field we can observe in nature. But the most dramatic breakthrough in black hole detection came with the development of gravitational wave astronomy. Suddenly, we gained the ability to detect black holes, not through their electromagnetic effects, but through their gravitational effects on spacetime itself. This opened up an entirely new population of black holes, those that exist in isolation or in purely gravitational binary systems, producing no visible light, but singing songs in the language of curved spacetime. The first gravitational wave detections revealed something surprising. The universe is full of black hole mergers involving objects with masses we hadn't expected to find. These stellar mass black holes, typically 20-50 times the mass of our Sun, exist in much larger numbers than previous surveys had suggested. It turned out that the universe had been conducting a vast symphony of black hole mergers, and we had simply been deaf to the music until we learned how to detect gravitational waves. Each gravitational wave detection is like receiving a postcard from the deep universe, carrying information about events so distant and ancient that the light from the host galaxies hasn't even had time to reach us yet. The waves travel unimpeded through space, carrying their messages across billions of light years without being absorbed, scattered, or distorted by intervening matter. What's particularly beautiful about gravitational wave detection is how it allows us to see the interior dynamics of the merger process itself. While electromagnetic observations show us only the periphery, the glowing gas and plasma around black holes, gravitational waves carry information from the heart of the event, from the region where spacetime itself is being most dramatically distorted. This has led to the development of what scientists call multi-messenger astronomy, using both gravitational waves and electromagnetic observations to study the same cosmic events. When LIGO detected the collision of two neutron stars, electromagnetic telescopes around the world quickly turned toward the same region of sky, capturing the optical, infrared, and gamma-ray afterglow of the event. For the first time, astronomers could both hear and see a cosmic collision, creating a much richer understanding of the physics involved. But perhaps the most profound aspect of detecting the undetectable is what it tells us about the nature of observation itself. Black holes have taught us that visibility and detectability are not the same thing. Some of the most important objects in the universe, the ones that anchor galaxies, drive cosmic evolution, and create the most extreme physics laboratories nature has to offer, remain forever invisible to direct observation. This has pushed astronomy toward increasingly indirect methods of detection, forcing us to become more creative, more subtle, more attuned to the secondary effects and gravitational fingerprints that massive objects leave on their surroundings. In learning to detect black holes, we've learned to read the universe's body language, to interpret the cosmic signs and signals that point toward the presence of objects we can never directly observe. The techniques we've developed for black hole astronomy have applications far beyond black holes themselves. The same gravitational wave detectors that reveal black hole mergers also promise to detect the gravitational echoes of the Big Bang itself, while the precise orbital timing methods used to study galactic center black holes have applications in testing fundamental physics and searching for dark matter. In a sense, black holes have made us better astronomers by forcing us to develop observation techniques that don't rely on light. They've taught us to listen with our instruments, to feel with our detectors, to infer the presence of the invisible from its effects on the visible. They've expanded our definition of what it means to observe the universe. As you contemplate the darkness around you, remember that it's filled with invisible giants, whose presence shapes everything we can see. Black holes lurk in the centers of galaxies, anchor the cosmic web of large-scale structure, and occasionally announce their collisions through gravitational waves that carry their songs across billions of years of space and time. We live in a universe where the most influential objects remain forever hidden, detectable only through their effects on the cosmos around them. In learning to find the undetectable, we've discovered that the invisible universe is just as rich, just as dynamic, and just as beautiful as the universe of light and matter that first drew our eyes toward the stars. Merging singularities. When two infinities become one. There are some ideas in physics that feel comfortable, almost intuitive, like watching water flow downhill, or feeling the warmth of sunlight on your skin. And then there are concepts so strange, so far removed from everyday experience, that they seem to belong more to philosophy or poetry than to science. The idea of a singularity, a point where matter is compressed to infinite density and spacetime curvature becomes infinite, is definitely in the second category. Yet at the heart of every black hole lies one of these mathematical impossibilities, and when two black holes collide, we're confronted with perhaps the most profound question in physics: what happens when two infinities become one? Let's approach this gently. The the way you might approach a sleeping animal. You don't want to startle. A singularity isn't really a physical object in any sense we can easily visualize. It's more like, imagine trying to divide a number by 0 on a calculator. The mathematics breaks down, giving you an error message, because the operation doesn't have a meaningful answer within our normal framework of numbers. This is what happens to Einstein's equations at the center of a black hole. The mathematics of spacetime curvature approaches infinite values, suggesting that our normal understanding of space and time simply stops working. But here's the beautiful thing about physics. Even when our mathematical tools encounter infinities, nature seems to find ways to make sense of what's happening. During a black hole merger, the singularities don't collide in the way that two billiard balls might collide. Instead, something far more subtle and elegant occurs. As our two black holes complete their final spiral and their event horizons merge, the singularities inside each black hole exist in a region of space-time that's already so warped, so far from our everyday experience of geometry, that concepts like distance and direction become almost meaningless. The singularities don't travel through space to meet each other. Instead, the space containing them transforms in such a way that what was once two separate regions of infinite curvature becomes a single region. Think of it like this. Imagine you have two extremely deep whirlpools in a river, spinning so tightly that the water at their centers forms vertical columns extending down beyond sight. Now imagine the river itself changing, the bottom reshaping itself so that what were once two separate whirlpools gradually become part of a single larger, more complex vortex. The water doesn't leap from one whirlpool to the other. Instead, the very geometry of the riverbed transforms until there's only one whirlpool where there used to be two. This is roughly analogous to what happens to the singularities during a black hole merger. Except instead of water and riverbeds, we're talking about the fundamental structure of space-time itself. The process is guided by Einstein's field equations, which describe how matter and energy tell space-time how to curve, and how that curvature tells matter how to move. But we must admit something here. Our understanding of what actually happens to singularities during a merger pushes the very limits of current physics. General relativity, for all its elegance and success, wasn't designed to handle the extreme conditions where quantum effects become important alongside gravitational effects. At the scale of a singularity, we need a theory of quantum gravity, a unified description of how quantum mechanics and general relativity work together, and we don't have such a theory yet. What we do know is that the merger creates a new singularity, presumably more massive than either of the original ones, sitting at the center of the newly formed black hole. This new singularity inherits properties from both of its parents, their combined mass, their angular momentum, and their electric charge. Though black holes in nature are thought to be electrically neutral, there's something almost mystical about this process when you really think about it. Two objects, each containing regions where the normal laws of physics break down, somehow combine to create a single object with similar properties. It's like watching two impossible things merge to create a single, slightly different impossible thing. Cosmic fireworks without light. Why there's no explosion? When we think about cosmic collisions, our minds naturally drift toward the spectacular. Exploding stars that outshine entire galaxies, asteroid impacts that leave glowing craters, comets that streak across the sky in brilliant displays of vaporizing ice and rock. There's something deeply satisfying about the idea that the universe's most powerful events should also be its most visually dramatic. That energy and spectacle should go hand in hand. This is what makes black hole collisions so beautifully paradoxical. Here we have events that release more energy in their final seconds than all the stars in the observable universe combined. Yet they produce no light, no explosion, no electromagnetic fireworks whatsoever. They are the universe's most powerful silent films, cosmic dramas played out in perfect darkness. To understand why this is, we need to think carefully about what an explosion actually is. When we see a firework burst in the sky, what we're really seeing is matter being rapidly heated to temperatures where it emits visible light. The chemical energy stored in the explosive compounds gets converted to kinetic energy of expanding gases, and those hot gases glow with thermal radiation. The same basic process occurs in supernovas, where nuclear energy heats stellar material to billions of degrees, creating light shows visible across intergalactic distances. But black holes are fundamentally different beasts. By definition, they are regions of space-time where the gravitational field is so strong that nothing, not matter, Not energy, not even light itself can escape once it crosses the event horizon. This means that any material that gets caught up in a black hole collision simply disappears from the observable universe without contributing to any kind of electromagnetic display. Let's imagine what happens to any matter that might be in the vicinity of two colliding black holes. Perhaps there are some stray gas clouds, dust particles, or even entire stars that happen to be caught between the two gravitational giants as they spiral toward each other. As the collision approaches, this material experiences tidal forces so extreme that atomic nuclei themselves get stretched and distorted. But instead of heating up and glowing like material in a conventional explosion, it simply gets swept up by the event horizons and vanishes from sight. It's like watching two invisible whirlpools merge in a dark pool of water. Any leaves or debris on the surface might get pulled into the vortex, but they don't create light or sparks. They simply disappear into the depths. The energy of their motion gets added to the energy of the whirlpool system, but there's no visible signature of their fate. This absence of electromagnetic radiation makes black hole collisions fundamentally different from every other high-energy astrophysical event we know about. Gamma-ray bursts announce themselves with beacons of electromagnetic energy visible halfway across the universe. Supernovas create expanding shells of glowing gas that shine for years. Even the more mundane processes of stars forming or planets colliding produce heat and light as gravitational energy gets converted to thermal energy. But the energy released in a black hole collision takes an entirely different form. Instead of heating matter to produce electromagnetic radiation, the energy goes into distorting space-time itself, creating gravitational waves that propagate outward at light speed. It's as if the universe has learned two completely different ways to release energy: the familiar way that produces light and heat, and this exotic way that produces ripples in the geometry of space and time. Think of it like this. Imagine two master sculptors working with completely different materials. One works with clay that glows when shaped, creating beautiful luminous sculptures that announce their creation with light and color. The other works with the invisible fabric of space itself, creating equally beautiful and far more energetic sculptures that remain forever invisible to electromagnetic eyes, but can be felt through their gravitational influence. The lack of electromagnetic signature also means that black hole collisions can happen anywhere in the universe without prior announcement. Unlike supernovas, which astronomers can sometimes predict by watching the evolution of massive stars, or gamma-ray bursts, which are often preceded by detectable electromagnetic activity, black hole mergers give no advance warning. They simply happen, releasing their gravitational wave signature into the cosmos, without any accompanying light show to herald their approach. This has profound implications for how we study these events. Traditional astronomy relies heavily on electromagnetic radiation, visible light, radio waves, X-rays, and so forth. But black hole collisions forced us to develop an entirely new kind of astronomy, based on gravitational radiation, using detectors that measure the stretching and compressing of space itself, rather than the arrival of photons. In a sense, black hole collisions exist in a parallel universe of pure gravity, disconnected from the electromagnetic universe that dominates our everyday experience. They represent cosmic events of tremendous power and significance that remain completely invisible to traditional telescopes. It's as if nature has been conducting a secret symphony of gravitational waves, and we only recently learned how to hear the music. But there's something almost elegant about this invisibility. Black hole collisions don't overwhelm their surroundings with violent explosions or disruptive radiation. Instead, they release their energy in the most gentle way possible, as gravitational waves that pass through matter without disturbing it, carrying their message across cosmic distances without heating, ionizing, or otherwise affecting the material they encounter. This gentleness means that gravitational waves serve as perfect messengers, carrying information about their sources across billions of light years, without degradation. Unlike light, which can be absorbed by dust, scattered by gas, or redshifted by cosmic expansion, gravitational waves arrive at Earth with their original frequency spectrum intact, providing us with an unobstructed view of events that happened when the universe was much younger. The absence of light from black hole collisions also highlights something profound about the nature of information in the universe. We're accustomed to thinking that information travels on electromagnetic waves, light carrying images to our eyes, radio waves carrying sounds to our ears, X-rays carrying structural information about the objects that emit them. But gravitational waves represent an entirely different information channel, one that existed in nature long before we learned to detect it. In some ways, the darkness of black hole collisions makes them more mysterious, and therefore more compelling. There's something haunting about the idea that the universe's most powerful events happen in perfect silence and invisibility, detectable only through their influence on the geometry of space-time itself. They remind us that reality extends far beyond what we can see, that the universe contains phenomena so exotic they challenge our basic assumptions about cause and effect, energy and matter, visibility and existence. Perhaps most remarkably, this darkness is not a limitation or a flaw. It's an essential feature of what black holes are. The same physics that makes black holes such powerful gravitational sources also ensures that their most dramatic moments remain invisible. They are cosmic events that exist purely in the realm of space-time geometry, divorced from the material universe of atoms and photons that produces all the light, shows we're familiar with. As you settle into the darkness of your own evening, consider that somewhere in the universe, events more powerful than supernovas are happening in complete silence. Black holes are colliding, releasing energies that dwarf the output of entire galaxies, yet producing no light, no heat, no electromagnetic signature of any kind. They are the universe's most spectacular invisible events, cosmic explosions that aren't explosions, fireworks displays written in the language of curved spacetime rather than glowing matter. The universe, it turns out, has learned to be dramatic without being loud, powerful without being bright. In the darkness between the stars, gravitational giants perform their ancient dances, release more energy than human minds can easily comprehend, and do it all in the most profound silence imaginable. They remind us that the most important events in cosmic history might be the ones we can't see, the ones that happen in dimensions of reality we're only just beginning to explore. Does time break during a collision? There are moments in life when time seems to behave strangely. When you're falling and a single second stretches into what feels like an eternity, or when you're deeply absorbed in something you love, and hours pass like minutes. We usually dismiss these experiences as psychological, tricks of perception rather than genuine alterations in the flow of time itself. But near black holes, especially during the violent dynamics of collision, time really does behave in ways that challenge our deepest intuitions about the nature of temporal flow. Einstein taught us that time isn't the universal, unchanging backdrop we once thought it was. Instead, time is woven together with space into a single fabric that can stretch, compress, twist, and bend in response to mass and energy. Near massive objects, time runs slower than it does in empty space. Near accelerating objects, time flows differently than it does for objects at rest. And, near colliding black holes, time undergoes contortions so extreme that our normal concepts of past, present, and future begin to lose their meaning. Let's begin with something called gravitational time dilation, the way that time runs slower, in stronger gravitational fields. If you could somehow position yourself at a safe distance from two colliding black holes and watch the collision through a telescope, you would notice something peculiar about the light coming from any matter near the black holes. That light would appear redshifted, stretched to longer, redder wavelengths. Not because the matter is moving away from you, but because time itself is running slower in the intense gravitational field near the black holes. This time dilation becomes more extreme as you get closer to the black holes. At the event horizon, that invisible boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. This creates one of the most mind-bending aspects of black hole physics. If you could watch someone fall into a black hole, you would never actually see them cross the event horizon. Instead, you would see them slow down, their image growing redder and dimmer as the light they emit becomes increasingly stretched by the gravitational time dilation, until they fade from view entirely. But during a black hole collision, even this strange behavior becomes more complicated. The gravitational field around two spiraling black holes is not static, it's dynamic, oscillating, changing rapidly as the black holes orbit each other at increasing speeds. This means that the time dilation effects are also oscillating, creating regions where time speeds up and slows down in complex wave-like patterns. Imagine trying to synchronize your watch while riding a roller coaster that's going through loops and corkscrews at nearly the speed of light. The acceleration and deceleration would cause your watch to run fast during some portions of the ride and slow during others, with the effects becoming more extreme as the ride gets faster and more chaotic. This is roughly analogous to what happens to the flow of time in the vicinity of colliding black holes, near the moment of merger. When the two black holes are orbiting each other hundreds of times per second, the oscillating time dilation effects become so rapid and so extreme that the very concept of a universal now breaks down completely. Different regions of space experience different rates of temporal flow, and these rates are changing so quickly that there's no meaningful way to synchronize clocks across the collision region. But perhaps the most profound temporal strangeness occurs inside the event horizons themselves. Once matter or energy crosses the event horizon of a black hole, it exists in a region where the normal relationship between space and time has been fundamentally altered. In some sense, the spatial direction inward toward the singularity becomes time-like, while the temporal direction becomes space-like. This is a deep mathematical result of general relativity that's almost impossible to visualize or understand intuitively. During the collision, as the event horizons merge and reshape themselves, these regions of altered spacetime topology undergo complex interactions. What was once the interior future of one black hole becomes connected to the interior future of another, creating a unified region where the normal flow of causality, the rule that causes must precede their effects, becomes ambiguous. Some physicists have speculated that the interior of a merging black hole might contain closed time-like curves, paths through spacetime that loop back on themselves temporally, potentially allowing effects to precede their causes. While such curves are mathematically possible solutions to Einstein's equations, most physicists believe that quantum effects would prevent them from actually forming in nature. The universe seems to have built-in safeguards against causal paradoxes, though the exact nature of these safeguards remains mysterious. Another temporal puzzle arises when we consider the information paradox in the context of black hole mergers. If black holes contain information about everything that has ever fallen into them, what happens to that information when two black holes merge? Does the information from both black holes somehow combine, or does some of it get lost? And how does this process unfold in time, given that time itself is flowing differently inside the event horizon than it does outside? Recent work in theoretical physics suggests that black holes might not be the information destroyers we once thought they were. Some theories propose that information falling into a black hole becomes encoded on the event horizon itself, spread out across the surface in a way that preserves it, even as the black hole evaporates through Hawking radiation. During a merger, this surface information from two black holes would combine in complex ways, potentially creating new forms of information storage and processing that we're only beginning to understand. But perhaps the most beautiful aspect of time near colliding black holes is how it illustrates the deep connection between gravity and geometry that lies at the heart of general relativity. Time doesn't break during a collision so much as it reveals its true nature as part of the geometric structure of the universe. The strange temporal effects we observe are not glitches or failures of physics. They're features, natural consequences of the way mass and energy curve the spacetime in which they exist. This geometric understanding of time has profound implications for how we think about the collision process itself. From our perspective as distant observers, the collision unfolds over a period of perhaps a few seconds. The time it takes for the gravitational wave signal to rise in frequency, peak at the moment of merger, and then fade away during the ring-down. But from the perspective of observers at different distances from the black holes, the same collision might appear to take vastly different amounts of time. There's no single universal timeline for a black hole collision because time itself is part of what's being distorted by the event. Instead, there are many different temporal perspectives, each equally valid within its own reference frame. The collision exists not as a single event happening at a specific time, but as a complex pattern of causally connected events spread across the curved spacetime around the merging black holes. In some sense, asking whether time breaks during a black hole collision is like asking whether a river breaks when it flows around a rock. The river doesn't break, it simply follows the contours of the landscape through which it flows. Similarly, time doesn't break near colliding black holes. It simply follows the contours of the curved spacetime created by the enormous masses and energies involved in the collision. This perspective suggests that the extreme temporal effects near black hole collisions might actually be windows into the fundamental nature of time itself. By studying how time behaves in these most extreme environments, we're learning about the deep structure of temporal reality, discovering aspects of time's nature that remain hidden in the gentler gravitational fields of everyday experience. As you drift toward sleep, consider that time itself is more flexible, more dynamic, more mysterious than our everyday experience suggests. Near colliding black holes, past and future become tangled with space and causality in ways that challenge our most basic assumptions about the nature of temporal flow. Yet somehow the universe manages to maintain its coherence even in these extreme conditions, following mathematical laws that remain elegant and consistent even when time itself seems to lose its familiar characteristics. The collision of black holes doesn't break time, it reveals time's hidden depths, showing us that what we experience as the steady, universal flow of temporal succession is actually part of a much richer, more complex structure that connects time, space, gravity, and geometry in ways we're still learning to understand. Picture yourself standing at the edge of a still pond on a quiet morning. You drop a stone, and ripples spread outward in perfect circles. Now imagine that stone is not a pebble, but something so massive, so dense, that it bends not just water but the very fabric of reality itself. This is where our journey takes us deeper, to the edges of existence, where even the concept of edge becomes something altogether more mysterious. Event horizon distortions, the stretching of the edge. You know that feeling when you're stretching a rubber band, watching it grow thinner and longer until you wonder if it might snap? The event horizon of a black hole, that invisible boundary, where escape becomes impossible, behaves something like that rubber band during a collision, except infinitely more strange. The event horizon isn't really a physical thing you could touch, despite how we imagine it. It's more like the point of no return at the top of a waterfall, except this waterfall flows through dimensions we can barely comprehend. As two black holes spiral toward each other in their final dance, their event horizons begin to stretch and distort like taffy being pulled by invisible hands. Imagine if you could paint the surface of a soap bubble, then slowly push two other bubbles against it from opposite sides. The surface would bulge and stretch, creating these beautiful, impossible curves. The event horizons do something similar, but in a space where up and down lose their meaning, where the very notion of surface becomes a whisper of mathematics rather than something you could walk on. During those final moments before merger, and we're talking about seconds that contain more drama than entire centuries of human history, the event horizons stretch toward each other like two lovers, reaching across an impossible distance. They form what scientists poetically call a bridge, though it's a bridge built not of stone or steel, but of curved space-time itself. The stretching happens because space-time around each black hole is already severely warped, like a bowling ball placed on a trampoline. When two such distortions approach each other, they don't simply add together the way you might expect. Instead, they create interference patterns, like waves meeting in that pond we imagined. But these waves are made of the fabric of reality itself, and here's where it gets wonderfully peculiar. The event horizon can actually grow larger than you'd expect from simply adding two black holes together. It's as if the universe is making room for something new, something unprecedented. The total area of the merged event horizon will always be larger than the sum of the original two, a rule so fundamental that physicists call it the area theorem, though it sounds more like a promise the universe makes to itself. But what does this stretching mean for anything nearby? Well, if you were an intrepid space traveler observing from a safe distance, and we're talking about a very, very safe distance, you'd witness something like watching two whirlpools merge in slow motion. Except these whirlpools are made of space and time themselves. The distortions would be so severe that light itself gets bent and twisted, creating a funhouse mirror effect across the cosmos. And that brings us to one of the most haunting questions in all of astrophysics. Can anything escape a merging black hole? There's something almost heartbreaking about the finality of a black hole's grip. Once something crosses that event horizon, it's gone. Not just hidden from view, but removed from our universe's story entirely. Or so we thought, until we started understanding the beautiful complexity of black hole collisions. During a merger, something extraordinary happens. Picture two soap bubbles joining just before they become one. There's a moment where they're connected but not quite unified. In that instant, the rules become flexible. The event horizons touch and merge, creating temporary distortions that behave like cosmic escape routes. Think about water flowing down a drain. Normally, once water gets close enough to the center, it's doomed to spiral inward. But if you could somehow disturb the drain just right, shake the whole sink, perhaps some of that water might splash back out. Black hole mergers create disturbances so violent they can, in a sense, shake space-time itself. The gravitational waves generated during collision don't just carry away energy, They can actually fling matter outward at tremendous speeds. It's as if the universe is so shocked by the violence of the merger that it reflexively throws some of the black hole's accumulated matter back into space. These kicks can be so powerful that they can eject the newly formed black hole from its home galaxy entirely, sending it wandering through the cosmic void like an exile. But here's the truly fascinating part. The information that fell into those black holes long ago, the quantum fingerprints of every star, every planet, every speck of matter they consumed. Where does that go? This is what physicists call the information paradox, and it's one of those questions that keeps brilliant minds awake at night, staring at the ceiling and wondering about the true nature of reality. Some theories suggest that during the chaos of merger, this information might somehow be encoded in the gravitational waves themselves, like messages in bottles cast into the cosmic ocean. Others propose that the information gets smeared across the event horizon in ways so subtle that we'd need technologies we can't even imagine to detect them. It's like asking whether a poem still exists after you've burned the paper it was written on. The words are gone, but did something essential, some pattern, some meaning, somehow escape into the smoke? The collision of black holes forces us to ask these kinds of questions about the fundamental nature of information, memory, and existence itself. And speaking of things that seem to vanish, the mass that disappears, where does it go? Here's something that would have made Einstein smile with that mischievous gleam in his eye. When two black holes merge, some of their mass simply disappears. Not literally, of course. The universe is far too well organized for that kind of accounting error. But it vanishes from the merged black hole in a way that's both beautiful and profound. Imagine you're at a cosmic garage sale, and the universe is cleaning house. You have two black holes, each with their own mass, their own gravitational influence, their own way of bending space-time. Logic suggests that when they combine, you'd get a new black hole, with exactly the sum of their masses. But the universe has other plans. Einstein taught us that mass and energy are two faces of the same coin. That famous E-C-Pel relationship that sounds simple, but contains multitudes. During a black hole merger, some of that mass gets converted into pure energy and radiated away as gravitational waves. It's like the universe is paying an exit fee, using mass as currency to fund the spectacular light show of space-time ripples. The amount of mass that gets converted is staggering. In the first gravitational wave detection by LIGO, 3 solar masses, 3 times the mass of our entire sun, vanished in the final fraction of a second before merger. That's like the universe making 3 suns worth of matter disappear in the blink of an eye, transforming it into waves that stretch and squeeze space itself as they propagate outward. But where does this energy actually go? Picture throwing a stone into that still pond again. The stone disappears beneath the surface, but its energy doesn't vanish. It spreads outward as ripples, carrying information about the splash to distant shores. The gravitational waves from a black hole merger behave similarly, carrying energy across billions of light years, making tiny but measurable changes to the distance between objects as they pass. This energy doesn't just disappear into nothing. It joins the cosmic background, becoming part of the universe's fundamental vibration. Every black hole merger in cosmic history has contributed to a kind of gravitational symphony that's always playing around us, too quiet for us to hear without the most sensitive instruments ever built, but always there, like the universe humming to itself. And in a poetic sense, this means that the matter that formed those original black holes, perhaps born in the hearts of the very first stars, forged from hydrogen that condensed from the primordial soup of the Big Bang, doesn't truly die. It transforms, becoming waves that will travel across the cosmos until the end of time, carrying the signature of that merger to civilizations and worlds not yet born. It's the universe's way of ensuring that nothing is ever truly lost, just converted into something more ethereal, more fundamental. And that energy, those gravitational waves, they don't just travel aimlessly through space, they reshape everything they touch, including the galaxies themselves. How black hole collisions reshape galaxies. Think about how a single raindrop can change the course of a river, given enough time and the right conditions. Now, imagine that raindrop is a collision between objects so massive that they can barely be comprehended. And the river is an entire galaxy containing hundreds of billions of stars. This is the scale we're talking about when we consider how black hole mergers reshape the cosmic landscape. Every galaxy hosts a supermassive black hole at its center, a gravitational anchor that helps hold the entire galactic family together. These aren't just passive residents, they are active participants in their galaxy's life story. influencing star formation, gas flow, and the overall structure of their cosmic neighborhoods. When two galaxies merge, a process that unfolds over hundreds of millions of years, their central black holes eventually find each other in a cosmic dance that reshapes everything around them. Picture two vast whirlpools slowly approaching each other in an ocean. As they get closer, the water between them becomes increasingly turbulent, creating currents and eddies that affect everything in the vicinity. Similarly, as supermassive black holes spiral toward collision, they create gravitational disturbances that ripple through their galaxy, triggering bursts of star formation, flinging stars into new orbits, and fundamentally altering the galactic architecture. The gravitational waves from the final merger can actually kick the newly formed black hole out of the galaxy's center, like a cosmic billiard ball struck by an invisible cue. Imagine the central organizing force of a galaxy, something millions or billions of times more massive than our sun, suddenly flying off into space at thousands of kilometers per second. The galaxy is left spinning around an empty center, its structure forever changed by this single violent event. But the influence extends far beyond the immediate vicinity. The energy released during collision can heat up gas throughout the galaxy, preventing new stars from forming for millions of years. It's like the merger creates a cosmic winter, temporarily halting the galaxy's ability to renew itself. Other regions might experience the opposite effect. Compression waves from the collision could trigger massive bursts of star formation, creating brilliant stellar nurseries that light up the galaxy like cosmic fireworks. Some astronomers believe that these collisions might be responsible for creating the different types of galaxies we see today. The elliptical galaxies, with their smooth, featureless appearance, might be the result of ancient mergers that thoroughly mixed and disrupted the orderly spiral structures their predecessors once had. It's as if the universe is an artist who sometimes decides to blend their careful brushstrokes into something entirely new. And then there's the mysterious influence we can't see directly, the role of dark matter in the collision ballet. There's an invisible partner in this cosmic dance, something that makes up most of the matter in the universe but refuses to interact with light in any way we can detect. Dark matter is like the silent choreographer of galactic collisions, shaping the movements without ever stepping into the spotlight. Imagine trying to understand a dance by only watching one of the two dancers. You'd see graceful movements and dramatic spins, but you'd miss the subtle pushes and pulls, the way one partner guides the other through steps you can't quite follow. This is what it's like studying galaxy mergers without accounting for dark matter. The visible matter, stars and gas clouds, follows patterns that only make sense when you remember there's 5 times as much invisible matter, orchestrating the entire performance. Dark matter doesn't just sit passively in the background. During a galactic merger, the dark matter halos that surround each galaxy interact in complex ways, creating gravitational fields that guide the paths of the supermassive black holes toward their eventual collision. It's like having invisible rails that determine where the cosmic train will go, even though we can only see the train itself. The dark matter also acts as a kind of cosmic cushion, absorbing some of the gravitational energy from the black hole merger and helping to stabilize the resulting galaxy. Without this invisible buffer, many galaxy mergers might tear themselves apart entirely, scattering their stars across intergalactic space like cosmic dandelion seeds on the wind. Computer simulations of these mergers, vast calculations that require some of the most powerful supercomputers on Earth, show that the dark matter forms intricate patterns during collision streams and shells, and perfectly symmetrical structures that exist only in the gravitational realm, invisible to our eyes, but fundamental to understanding how the universe organizes itself. Some scientists speculate that the collision might even affect the dark matter particles themselves in ways we don't yet understand. Perhaps the extreme gravitational fields create conditions where dark matter can briefly interact with normal matter, or where the mysterious properties of dark energy, that other invisible component of the universe, come into play. These are questions at the very frontier of physics, where our best theories meet the limits of our understanding. And all of this invisible choreography creates something we can finally detect, a symphony that plays in dimensions we're only just learning to hear. The gravitational symphony. Listening to space bend. Music has always been mathematics made beautiful, patterns in time that speak to something deep within us. But the universe plays its own compositions on instruments we never imagined, using space-time itself as strings, black holes as percussion, and the fabric of reality as a concert hall that stretches across billions of light-years. When LIGO first detected gravitational waves in 2015, scientists didn't just see the data on their computer screens, They literally heard it. The signal, when converted to sound waves, our ears can process, sounds like a chirp, a brief whoop that rises in pitch before cutting off abruptly. It's the universe's recording of two black holes completing their billion-year courtship in a final violent embrace that lasted less than half a second. But calling it just a chirp is like describing Beethoven's Ninth Symphony as some organized noise. Each gravitational wave detection tells a story written in the language of warped spacetime. The frequency tells us how fast the black holes were spinning around each other. The rate at which the frequency increases reveals how quickly they were spiraling inward. The sudden cutoff marks the moment of merger, when two separate entities became one. Think about how a violin string creates music by vibrating back and forth, alternately compressing and expanding the air around it. Gravitational waves work similarly, except instead of moving air molecules, they stretch and squeeze space itself. As the waves pass through Earth, they make our entire planet ring like a bell, though the changes are so tiny that it took us a century after Einstein predicted them to build instruments sensitive enough to detect them. The LIGO detectors are actually the universe's most sensitive microphones, able to measure changes in distance smaller than 1/10,000th the width of a proton. Imagine trying to measure how the distance between Earth and the nearest star changes by less than the width of a human hair. That's the level of precision required to hear these cosmic concerts. Each detection adds another instrument to our growing orchestra of understanding. The heavier the black holes, the lower the pitch of their gravitational waves. Rapidly spinning black holes create more complex harmonics, like a skilled musician adding vibrato to a sustained note. When we detect multiple mergers, we can begin to hear the larger patterns. The cosmic background music that's been playing since the first stars collapsed into black holes billions of years ago. And just as human music can make us feel emotions we can't quite name, this gravitational symphony carries information about forces and phenomena that exist beyond our everyday experience. Some scientists believe that future detectors might be sensitive enough to hear the gravitational waves from the Big Bang itself, the universe's birth cry, still echoing through space-time after nearly 14 billion years. But what would happen if you found yourself in the front row of this cosmic concert? What would happen if you were nearby? There's something both thrilling and terrifying about imagining yourself as a witness to one of the most violent events in the universe. Of course, nearby is a relative term when we're talking about black hole mergers. Even being in the same galaxy would place you at what most cosmic standards would consider a safe distance. But let's indulge our curiosity and imagine what it might be like to observe this collision from various vantage points, each more impossible than the last. From a few thousand light-years away, roughly the distance to some of the nearest stars in our galaxy, the merger would be invisible to the naked eye. Black holes don't shine, and the gravitational waves, though carrying tremendous energy, would pass through you and your spacecraft like the gentlest of cosmic breezes. You might detect them with sensitive instruments, but you certainly wouldn't feel them. It would be like standing next to a silent explosion, aware that something monumentous was happening, but experiencing it only through the subtle trembling of your most delicate measuring devices. But move closer, say a few hundred light-years away, and the environment around the colliding black holes would put on quite a show. Any matter unfortunate enough to be orbiting these monsters would be heating up as tidal forces stretched and compressed it. This superheated material would glow brilliantly across the electromagnetic spectrum, creating a lighthouse beam of radiation that could outshine entire galaxies for brief moments. You'd witness auroras unlike anything Earth has ever seen, as charged particles accelerated to near light speed painted impossible colors across space. At a few dozen light-years away, things would become genuinely dangerous. The gravitational waves would now be strong enough to affect the structure of any planets, potentially triggering massive earthquakes and volcanic activity. The radiation from heated matter around the black holes would be intense enough to strip away atmospheric protection, turning any nearby worlds into sterile, irradiated rocks. It would be like watching creation and destruction dancing together in perfect, terrible harmony. But let's push our imagination to its absolute limits and consider what might happen if you were somehow protected and positioned just outside the event horizons during those final moments. Time would behave in ways that would make your head spin, literally. The immense gravitational field would stretch seconds into eternities and compress eternities into heartbeats. You'd experience time dilation so extreme that the rest of the universe would appear to speed up around you, stars being born and dying in what seemed like moments. The tidal forces would be indescribable. Your feet would experience significantly more gravitational pull than your head, stretching you like cosmic taffy. But in a strange way, this spaghettification would happen so smoothly, so gradually from your perspective, that it might feel almost peaceful, like being gently pulled apart by invisible hands while the universe rushed by and fast forward around you. And the visual effects would redefine the meaning of spectacular. Light from distant stars would be bent and twisted around the black holes, creating multiple images, Einstein rings, and gravitational lenses that would turn the cosmos into a funhouse mirror of reality. You might see the same star in a dozen different directions, or watch light that's been orbiting the black hole finally escape, carrying images from events that happened years or even decades ago. Of course, none of this is remotely survivable by any known physics or technology, but there's something beautiful about imagining ourselves as witnesses to these cosmic dramas, even if only in the realm of thought experiments. It connects us to the universe in a way that raw mathematics cannot, reminding us that we're not separate from these cosmic events. We're part of the same universe that creates them, made of atoms forged in stellar cores, living on a planet that rides through space on gravitational waves we're only now learning to detect. And speaking of connection to cosmic events, it turns out that black hole collisions weren't just rare, exotic occurrences. They may have been the universe's favorite way of making noise during its early wild youth. Collisions in the early universe. A common birth cry. Picture the universe as a newborn, not the serene, organized cosmos we see today, but a chaotic nursery where everything was smaller, denser, and far more violent. In those early epochs, when the universe was just a few 100 million years old, black hole mergers weren't rare, exotic events. They were as common as thunderstorms in summer, a regular part of the cosmic weather pattern. The first stars were unlike anything we see today. They were massive beyond our current comprehension, some containing hundreds of times more material than our sun, burning through their fuel so quickly that their entire lifetime spanned just a few million years. When these stellar giants died, they didn't go gently into that good night. They collapsed into black holes with a violence that sent shockwaves rippling through the primordial universe. But here's where the early universe was fundamentally different from today. Everything was much closer together. Galaxies were still forming, still gathering material, still figuring out their eventual shapes and sizes. In this crowded cosmic daycare, black holes found each other much more easily than they do in our current, more spacious universe. It was like a cosmic game of musical chairs, except the chairs were gravitational wells, and when the music stopped, black holes merged. These early mergers were the universe learning how to make music with spacetime itself. Each collision sent gravitational waves rippling outward, and since there were so many more collisions happening, the early universe was filled with a constant background hum of gravitational radiation, a cosmic lullaby that helped shape the formation of the first galactic structures. Some scientists believe that these frequent early mergers are responsible for seeding the supermassive black holes we find at the centers of galaxies today. Instead of growing slowly by consuming matter one star at a time, these monsters might have gotten their head start by merging repeatedly during the universe's turbulent childhood. It's like compound interest, but instead of money accumulating in a bank account, mass and energy were accumulating in increasingly powerful gravitational wells. The gravitational waves from these ancient collisions are still traveling through space today, carrying messages from a time when the universe was unimaginably different. They've been journeying through the cosmos for over 13 billion years, and some of them are reaching Earth right now, whispering stories of cosmic violence from an era when the first atoms were still settling into their eternal dance. Future gravitational wave detectors might be sensitive enough to hear this ancient cosmic background radiation, not the microwave radiation left over from the Big Bang that we already detect, but a deeper, more fundamental vibration that comes from the universe's first black holes, learning how to dance together. It would be like hearing the universe's first attempts at music, the cosmic equivalent of a child's first piano lesson. Clumsy, perhaps, but full of promise and power. And this raises a fascinating question about scale and significance. Supermassive versus stellar. Which collisions matter more? The universe has a way of operating on scales that make our human experience seem almost laughably small, and then going even further to create scales that dwarf our already humbled perspective. When it comes to black hole collisions, we're dealing with two completely different weight classes, each with its own cosmic significance. Stellar mass black holes, the remnants of individual stars that have collapsed, typically contain between a few and a few dozen times the mass of our sun. When they merge, They're like cosmic firecrackers, brief, intense, and detectable with our current technology. These are the collisions that LIGO and Virgo detect regularly, the ones that first opened our ears to the gravitational symphony of the universe. But then there are the supermassive black holes, monsters that contain millions or billions of solar masses, lurking at the centers of galaxies like sleeping dragons. When these titans collide, they don't just send ripples through spacetime. They create gravitational tsunamis that can be detected by space-based observatories and affect the structure of entire galactic clusters. So which matters more? It's like asking whether raindrops or rivers are more important to the water cycle. Stellar mass mergers happen far more frequently. We detect them almost weekly now, but each individual event has a relatively small impact on the large-scale structure of the universe. They're the universe's background percussion, keeping time while larger movements unfold. Supermassive black hole mergers, on the other hand, are rare, epochal events that can fundamentally reshape galactic neighborhoods. When two galaxy-sized systems merge, bringing their central black holes together, the process can take hundreds of millions of years and affect trillions of stars. These are the universe's symphonic movements, grand compositions that play out over cosmic timescales. From a purely gravitational wave perspective, stellar mergers are currently our bread and butter. They happen often enough that we can study them in detail, and they produce waves at frequencies our detectors are optimized to hear. But the real prize would be detecting supermassive black hole mergers, which produce waves so long that we need space-based detectors to hear them properly. The planned LISA mission, a space-based gravitational wave observatory, will be able to detect these supermassive mergers from across the observable universe. Imagine being able to hear every major galactic collision that's happened in the last 10 billion years, like having a cosmic time machine that lets us eavesdrop on the universe's most dramatic moments. But perhaps the most intriguing possibility is that both types of mergers are part of a larger cosmic story, with stellar mass black holes providing the building blocks and supermassive mergers providing the major plot points in the universe's ongoing narrative. It's like the difference between the individual words and the chapters in a vast cosmic novel, both necessary, both meaningful, but operating on completely different scales of significance. And this brings us to a question that's both humbling and thrilling to consider. Are we living in the afterglow of a collision? There's something haunting about the possibility that our entire existence might be shaped by cosmic violence that occurred long before the first humans looked up at the stars and wondered about their place in the universe. Every atom in your body, every breath you take, every thought you think, all of it might be riding on gravitational waves from black hole collisions that happened when the universe was young and wild. Think about how a pebble dropped in a pond creates ripples that eventually reach the shore, but by the time they arrive, they're so gentle that they barely disturb the reeds at the water's edge. Gravitational waves behave similarly. A violent collision between black holes, billions of years ago, would create massive distortions in spacetime that gradually spread outward, becoming gentler and more subtle as they travel across cosmic distances. By the time these ancient waves reach us, they're incredibly weak, too subtle to detect with current technology if they come from the very early universe. But that doesn't mean they're not affecting us. These waves are still stretching and compressing space-time around us, still influencing the fundamental geometry of reality at levels so minute that we can't measure them yet. But that might nonetheless be part of the cosmic background conditions that allow galaxies, stars, planets, and life to exist in their current forms. Our local group of galaxies, the Milky Way, Andromeda, and dozens of smaller companions, might have been shaped by supermassive black hole mergers that occurred during the early epochs of galactic formation. The particular way our galaxy spirals, the specific location of our solar system within it, even the conditions that allowed Earth to form in the habitable zone around a stable star, all of these factors might be influenced by gravitational waves from collisions that happened long before our solar system even existed. It's like discovering that the music you've been unconsciously humming your entire life is actually an echo of a symphony that was performed in another room years before you were born. The gravitational background of our universe carries the signatures of every major collision that's ever occurred, creating a kind of cosmic memory that influences everything without us realizing it. Some theoretical physicists have proposed that the accelerating expansion of the universe, driven by the mysterious dark energy, might be connected to the accumulated effects of gravitational waves from countless black hole mergers throughout cosmic history. It's a controversial idea, but it suggests that the collision events we're detecting today might be part of a feedback loop that affects the ultimate fate of the cosmos itself. Even more intriguingly, The quantum fluctuations that eventually grew into galaxies and stars might have been influenced by gravitational waves from the very first black holes formed after the Big Bang. If this is true, then the patterns we see in the cosmic microwave background, the afterglow of the Big Bang itself, might carry the fingerprints of primordial black hole collisions. This means we might quite literally be living in the afterglow of ancient cosmic violence, shaped by forces we're only now learning to detect and understand. Every time we measure a gravitational wave with LIGO or Virgo, we're not just observing a current event, we're connecting with a chain of cosmic cause and effect that stretches back to the universe's violent youth. And this connectivity points to something even more profound about the nature of space-time itself, black hole, mergers, and the fabric of the universe. Imagine trying to understand the nature of a vast invisible fabric by observing how it responds to being struck by cosmic hammers. That's essentially what we're doing when we study black hole mergers and their gravitational waves. We're learning about the fundamental structure of space-time by watching how it vibrates when subjected to the most extreme conditions in the universe. Einstein's general relativity tells us that space and time aren't separate entities, but aspects of a single unified space-time that can be bent, twisted, and stretched by mass and energy. But what does that really mean? How do you bend something that isn't made of any substance we can touch or see? Black hole collisions give us a way to probe this mystery directly. When two black holes merge, they create distortions in spacetime so severe that the very concepts of here and there, now and then become fluid and relative. The event creates conditions where spacetime behaves almost like a liquid, flowing and churning in ways that reveal properties we never suspected. The gravitational waves themselves are like sonar pings in this cosmic ocean, allowing us to map the hidden currents and depths of spacetime's structure. Each detection tells us something new about how this fundamental fabric responds to stress, how it carries information, how it interacts with matter and energy on the most basic level. Some of the most exciting discoveries have come from studying the ring-down phase of black hole mergers, the period just after collision when the newly formed black hole settles into its final state. During this phase, the black hole literally rings like a bell, vibrating in specific modes that depend on its mass, spin, and charge. By analyzing these vibrations, we can test whether black holes really behave exactly as Einstein predicted, or whether there are subtle deviations that might point to new physics. It's like being able to determine the composition and structure of a bell by listening to how it rings, except this bell is made of warped spacetime and its vibrations propagate at the speed of light across billions of years. The precision required is staggering. We're measuring changes in the fundamental geometry of reality that are smaller than the width of an atomic nucleus. These measurements are revealing that spacetime is far more dynamic and responsive than we ever imagined. It's not just a passive stage where cosmic dramas play out, but an active participant in the universe's evolution. The fabric itself carries energy, momentum, and information in ways that blur the traditional boundaries between matter, energy, and the space they inhabit. Some theoretical physicists speculate that spacetime might have its own complex internal structure, perhaps made up of more fundamental entities that we haven't discovered yet, or perhaps emerging from quantum mechanical processes that operate below the scale of direct observation. Black hole mergers might be giving us our first glimpses into these deeper layers of reality. The implications extend far beyond academic curiosity. Understanding the true nature of spacetime could unlock technologies we can barely imagine, ways of manipulating gravity directly, methods for storing and processing information in the quantum structure of space itself, or even approaches to faster-than-light communication through carefully orchestrated distortions in spacetime's fabric. But perhaps the most profound implication is philosophical. We're discovering that the universe is far stranger, far more interconnected, and far more alive than our everyday experience suggests. We're not separate observers studying distant phenomena, we're embedded in the same cosmic fabric that carries these gravitational waves, made of the same fundamental spacetime that bends and flows around black hole collisions. And this brings us to the deepest question of all, the end, or a new beginning. What mergers might reveal about creation? As we reach the end of our journey through the cosmic violence of black hole collisions, we find ourselves confronting questions that philosophers and physicists have wrestled with for centuries. What is the fundamental nature of existence? How did everything begin? And perhaps most intriguingly, how will it all end? Black hole mergers might hold clues to all of these cosmic mysteries. These collisions represent both ultimate destruction and creative potential. They destroy the individual identities of the merging black holes, while creating something new and more complex. It's like watching the universe's approach to renewal through apparent destruction. Some of the most speculative theories in modern physics suggest that black hole mergers might actually be connected to the creation of new universes. The extreme conditions during collision, where spacetime itself becomes fluid and quantum effects might dominate, could potentially create baby universes that bud off from our own reality, like soap bubbles forming in cosmic foam. This idea, while highly speculative, suggests that the violent events we observe might not be endings at all, but beginnings. Each black hole merger could be giving birth to entirely new realms of existence, complete with their own laws of physics, their own spaces and times, their own potential for developing complexity and even life. The information paradox we discussed earlier takes on new meaning in this context. Perhaps the information that falls into black holes doesn't disappear or get destroyed. Maybe it gets encoded in the structure of these newborn universes, becoming the foundation for entirely new forms of existence. It would be like the universe's ultimate recycling program, where nothing is ever truly lost, just transformed into something unimaginably different. Even if these speculations prove incorrect, black hole mergers are certainly revealing fundamental truths about the nature of time, space, matter, and energy. They're showing us that the universe is far more dynamic and creative than we suspected, constantly reshaping itself through processes so violent they can only be described in the language of poetry and mathematics combined. The gravitational waves we detect today carry information from the universe's past, but they also influence its future. Each collision changes the cosmic background ever so slightly, contributing to the evolving symphony of spacetime that will shape the formation of future galaxies, future stars, future worlds where future beings might stand and wonder at the night sky just as we do. And perhaps that's the most beautiful aspect of this entire cosmic story, the recognition that we are intimately connected to these distant, violent events. The carbon in our bodies was forged in stellar cores that might have ended their lives as black holes. The calcium in our bones might have been scattered by supernova explosions that created the very black holes we're now detecting as they merge billions of years later. We are made of star stuff, as Carl Sagan famously said, but we're also made of space-time itself. We exist within the same fundamental fabric that carries these gravitational waves across the cosmos. Every time we detect a black hole merger, we're not just observing a distant event, we're participating in a conversation that spans the entire history of the universe. The waves that stretch and squeeze our LIGO detectors today began their journey when the universe was young, traveling through billions of years of cosmic evolution to reach us at this precise moment in time. They've witnessed the formation of the first galaxies, the birth and death of countless stars, the slow assembly of the cosmic web that connects all things. And now they're here, whispering their ancient stories to our instruments, carrying messages from the universe's most violent moments to our quiet corner of spacetime. In a sense, black hole collisions represent the universe's way of processing its own memories. Each merger erases the individual histories of the colliding objects while simultaneously encoding that information in gravitational waves that will travel forever through space and time. It's like the cosmos is constantly rewriting its own story, destroying old chapters to make room for new ones, but never truly forgetting, always carrying the essential information forward in new forms. As we stand on the threshold of an era where gravitational wave astronomy will become as routine as optical astronomy, we're preparing to hear the universe's entire percussion section for the first time. Future detectors will be sensitive enough to hear black hole mergers from the very edge of the observable universe, allowing us to map the cosmic distribution of these events throughout the entire history of star formation and galactic evolution. But perhaps the most profound realization is that these collisions remind us that the universe is not a static, finished creation. It's an ongoing process of becoming. Every black hole merger changes the cosmic landscape in subtle but real ways, contributing to the universe's continued evolution and complexity. We're not just observers of this process, we're participants in it, products of it. And perhaps someday, when our sun expires and our galaxy merges with Andromeda, we'll become part of it in the most fundamental way possible. The story of black hole collisions is ultimately a story about connection, how the most isolated objects in the universe eventually find each other across impossible distances and merge into something new. It's about how violence and beauty can coexist on cosmic scales, how destruction and creation are often the same process viewed from different perspectives. And so, as we drift towards sleep, carried by the gentle rhythm of gravitational waves that have been traveling toward us since before the Earth formed, We can take comfort in knowing that we're part of something infinitely larger and more beautiful than our daily concerns. We're riding through space on a planet orbiting a star in a galaxy that's dancing slowly toward merger with its neighbor, all of it embedded in a space-time fabric that carries the signatures of cosmic collisions from the universe's violent and creative past. The next time you look up at the night sky, remember that you're not just seeing distant stars, you're seeing the visible traces of a universe that's been shaped by countless black hole mergers, each one contributing to the cosmic symphony that makes our existence possible. And somewhere out there, in the depths of space we can't even see, two more black holes are beginning their final dance, preparing to add their voices to the eternal song of space-time itself. In the end, that's what black hole collisions teach us, that even the most violent events in the universe are part of a larger harmony, a cosmic music that connects all things across space and time. We are not separate from this music. We are notes in it, brief but essential contributions, a symphony that began with the Big Bang and will continue long after our individual songs have faded into the quantum foam from which everything emerged, and to which everything will eventually return. And in that return, that final merger with the cosmos itself, perhaps we'll discover that the end was always a beginning, that destruction was always creation, and that the universe's greatest secret is not that it will someday end, but that it will find new ways to begin again forever, and always, in patterns too beautiful and complex for any single mind to comprehend, but perfect for the collective cosmic consciousness of which we are all, ultimately, inseparable parts. Sleep now, carried by waves that have traveled across the universe to reach you in this moment, knowing that you are connected to everything that has ever been, everything that is, and everything that will ever be, through the invisible threads of space-time that bind all existence into one magnificent, ever-evolving whole.